Hi everyone, and welcome to our mid-semester presentation on utilizing spatial information in static wireless networks. To provide a quick overview of what our project entails, we want to understand how integrating spatial information can mitigate the exposed node problem. If we recall from last time, the exposed node problem, which is demonstrated in this graphic on the slide, is when two nodes, S1 and S2, wish to transmit simultaneously to R1 and R2. The problem arises because S1 and S2 are within range of each other and pick up on each other's transmissions, and so can't both transmit simultaneously for fears of collisions at their respective receivers. Generally speaking though, R1 and R2 are out of range of S2 and S1 respectively, and so they could, in theory, transmit at the same time without any collisions. So to attempt to mitigate these problems, we wish to modify various lower layer protocols such as DCF's implementation of CSMA-CA and the exponential backoff, and then generate results through some sort of network, simulator, or physical network.
As a recap from our previous presentation, I'm going to help bring everyone back up to speed on the exposed node problem. John described it on the previous slide, but just to recap everything, this problem has its origins in the use of CSMA-CA and in signal attenuation that's inherent in wireless networks. The problem description is you have two sending nodes and two receiving nodes. A node that wants to transmit and is physically capable of transmitting decides that it must wait based off of the algorithm. So the effect of this problem is that network performance is reduced unnecessarily. Solutions are the 802.11 DCF protocol, which really just kind of pulls the system out of a unstable state and keeps everything flowing along. And then RTS-CTS was proposed, but it never really delivered on its promises to solve this problem. There are, of course, other solutions discussed in the literature, but nothing concrete, no full solutions, and definitely nothing implemented at this time. Again, as a recap, this was the slide that we showed in our previous presentation, but it's been modified to be kind of the big picture, high-level, abstract methodology. On the slide, you'll see a CSMA-CA algorithm that runs through just kind of the high-level steps of exactly what CSMA-CA is doing, and then again, the figure of the exposed node problem reiterated. The key to understand on this slide is that at a high level, we want to modify simply the block wait for random backoff time. Rather than immediately jumping directly into that, as is done in the traditional DCF protocol, we want to integrate spatial information and determine whether a backoff is actually necessary. If it is, we'll follow the traditional DCF protocol, else we will perform our own protocol. That was the recap. And now we're going to transition into all of the work that we've done leading up to now.
So in order to implement our protocol modifications and generate any results, we had to either modify the relevant source code on our physical devices or utilize any tools provided in a network simulator. We ended up choosing the latter option and specifically focused on the NS3 network simulator for this project. So what is NS3? At its core, NS3 is a discrete event simulator with robust libraries that allow us to generate output, which we can then use in a packet trace analysis tool to analyze our results. NS3 is created around a modular design structure, and the core to any network topology centers around the abstractions of nodes, applications, channels, and net devices. Nodes are the basic computing device abstraction, and on these nodes you install applications which then generate any sort of traffic that you wish to send. This traffic then gets sent across a channel object, which essentially simulates any sort of physical channel that you might want to transmit across. And then net devices are the network interface card representation and network device drivers.
Diving deeper, I'm going to attempt to provide some background and some working knowledge to all of you about exactly how NS3 encapsulates and handles the emulation of a network interface card and network interface controller. So on the entire network interface card, NS3 breaks down the functionality at the PHY and data link abstract levels into a Wi-Fi net device that encapsulates the entire thing and provides a homogeneous interface to the higher levels, the transport and network layers. And it then proceeds to break down all of these steps into what seem to be their own kind of layering and sub-layering structure, but a lot of it overlaps with what is seen in the literature and I believe what is done in industry. As you can see on the left, the lower levels can be broken down into the MAC level, which includes the MAC high layer and the MAC low layer. On the graphic, MAC high is labeled as MAC high in the block, and the MAC low layer includes Channel Access Manager, TXOP, MAC RX middle, and MAC low. And then finally the PHY layer is the Wi-Fi PHY, which communicates directly with the physical channel. So breaking this down further, we're going to kind of jump around and discuss things, but this ordering makes sense because it deals with the less important modules leading all the way to the more important modules. So to start, the MAC high layer. This implements non-time critical Wi-Fi processes and models STAs, or stations, in an ad hoc mode. We chose the ad hoc Wi-Fi MAC class, which was one of the options in NS3. The MAC low sublayer, which is delineated by the box MAC low, implements RTS, CTS, data, and ACK transactions. And then the PHY layer models packet reception and tracks energy consumption. The creators of NS3 implemented all of these things to match as closely as possible actual physical wireless network interface cards and the IEEE 802.11 specifications. So now we're going to discuss the most important layer, which is the MAC middle sublayer, seen directly in the middle of this diagram with Channel Access Manager, TXOP, and MAC RX middle. The focus is on Channel Access Manager and TXOP, at least in terms of our project. Channel Access Manager implements DCF and contains most of our protocol modifications, as you'll see on a later slide. TXOP handles the packet queue, packet fragmentation, and packet retransmissions. Therefore, TXOP is a module that just gets handed packets from higher levels and queues them and waits until Channel Access Manager grants it access to the medium according to DCF, and then it will hand this data off to the lower level ones, MAC low, Wi-Fi PHY, who then have green lights all the way to begin transmission. And finally, MAC RX middle handles some intermediate processing operations during packet reception. So now to understand the changes that we made. All of the changes that we made, all of the relevant changes that we made occurred in the Channel Access Manager, which we actually made our own class, aptly named Modified Channel Access Manager. But one thing that I do kind of want to harp on here is the quote at the top of the slide. I'm not going to read the quote to you, but essentially what it says is it's taken directly from the documentation of NS3, saying that if you want to modify channel access management, that all of your changes are going to occur in Channel Access Manager. While this is almost true, it actually ended up being kind of a nightmare, and interoperability was an absolute mess. If you tried to modify the Channel Access Manager at all, it seemed like everything broke. But we were able to fix those problems and actually get our modified DCF algorithm to work. So now, as piggybacking off of the previous abstract methodology slide, we're now going to dive directly into the details with this graphic of the DCF algorithm. So we follow DCF exactly until the case when a node has data to transmit and the channel is found to be busy. Our modified algorithm then kicks in and performs calculations based off of spatial information that has structures within NS3 to make it easy to keep track of these spatial information and to calculate relevant interference ranges based off of the transmission power and the location of nodes. So we perform these calculations and we ask the question, is the interference avoidable? If the interference is avoidable, then the node that wants to transmit and sense the channel to be busy decides to go ahead and send underneath the cover of whatever node is currently transmitting, because that node has already performed all of the necessary DCF algorithms and has already claimed the channel. So everyone else is going to respect that. And we found out that we can slide our communication kind of overlapping under theirs without interfering with their communication, which is dominating the channel at this point in time. If we find that the interference is unavoidable, then we comply with 802.11 DCF, which is reproduced at the bottom of the slide, where we will generate a random backoff time within our contention window. We'll wait until the channel is clear, then wait a DIFS, which is a DCF interframe space, and then finally, we will wait our backoff time within the following contention window before we consent. And of course, that procedure is only followed assuming that that entire time no new transmitter tries to access the medium.